so bad for you.
What's the next one?
I don't know. It's really interesting. I don't really know how to describe it.
Hypothesis testing for proportions.
Yeah. So, I heard a couple of things about accessing the data. There might have been a typo in one letter or something like that, and so fix that. Things was there. I was rewriting some of the loops and some of the code that worked out. And so, and in general, as things come up, let me know if you can fix things, send it out to others, things like that. So in hypothesis testing proportions, we went over it quickly in an example, but I want to show a few more details on this one and talk about the continuity correction issue that's done for some of the binomials sometimes, right? So in this case, we're comparing, comparing two proportions. So we have two samples. Indeed, samples. So in one group, there's a proportion P1, and the other one there's a proportion P2. Two different subgroups, two different populations, two different time periods, independent samples each time, so not matched pairs. And we're interested, are these the same or are they different, and kind of what's the magnitude of the difference, right? So if each one is, if the things that we're measuring are success or failure, and we're going to have a count, x1 is some count. We're going to assume it has this binomial distribution, a binomial experiment. So there's N1 trials and a probability P1 of successes in that group. Independently in the other group, there's going to be an x2, which is going to be a count of successes, which is a binomial random variable with N2 trials and a probability of success P2 on each one. And based on the separate samples, P1 hat is going to be x1 over n1, the sample proportion there, and P2 hat that we're going to use is x2 over n2, the sample proportion there. And so for the difference, right, we're going to take the difference of these two things to estimate the difference of P1 and P2. So either we're going to do a confidence interval for the difference, or we're going to do a hypothesis test, which ultimately will be based on a calculation of that difference. So our estimate of P1 minus P2 is our P1 hat minus P2 hat, right? Our difference in sample proportion. Right? So if we're doing either confidence intervals or hypothesis tests, we think about the sampling distribution. Right? What would this difference look like if we had multiple independent samples from these distributions and took the difference many, many times into independence, right? Well, so we're focusing on the sampling distribution of P1 hat minus P2 hat, and that's where our inference comes from. If samples are not so small, right, so that the expected number of successes and the expected number of failures in both groups is not so small, right? So you neither one, P1 or P2, is too close to the edge with a small sample size. Then the sampling distribution of P1 hat, right, is approximately normal distributed. That's a central limit theorem application because the sample proportion is like an average. And averages in moderate-sized samples are kind of normally distributed in their likely outcomes. The expected value, the mean, is P1 minus P2. And the variance is the sum of the variances of these two estimates. And the minus becomes a plus because everything's in squared. In variances, so we have P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. Right? And that's the variance. If you have the square root, it's the standard deviation of those things. And so we base a confidence interval for this P1, P2 on P1 minus P2 hat plus or minus a normal multiplier like 1.96 times an estimate of this standard error. And the traditional thing to do is just plug in P1 hat or P2 hat in there. So based on that sampling distribution, we create a 95% confidence interval for P1 minus P2, as long as the samples aren't too small, of P1 hat minus P2 hat, plus or minus a normal value, say 1.96. And the formula for the standard error is the square root of this thing, but we're not going to know that exactly, but we're going to plug in our little estimators here. So in the example from Wednesday, there was 552 people surveyed in the Midwest, and of those, 62% reported approval of same-sex marriages, and N2 was 577 people in the West. And the estimate there was 68%. And so if we wanted to compare these regions, is there a difference between Midwest and West? We can take the difference. So our estimated difference can be 0.62 minus 0.68, so negative 0.06. If I do it this way, so this is Midwest minus West, so the negative value means that the Midwest is lower, or it means the West is higher. So there's a 6% difference in the samples. Right? And if we want to do a confidence interval, then we plug in the relative numbers into this and then get that number. Right? So I typed a little bit of that into R, so we spend so much time going through it. I reversed it from what I just said. Let's put that. So this first formula would be that estimate of the standard error, right? So the 0.62, 1 minus that is 0.38 in the sample size, plus the 0.68, 1 minus that, 577. So the standard error for that estimate is about 0.0288. Right? That's not the full margin of error, right? Because we're going to take the normal value times it, because normals are usually plus or minus about 1.96. So the margin of error is 0.056. Right? Usually for sample size planning, if you want one sample and you think about a margin of error plus or minus 0.5, it comes out to be about 384 sample. But because we have two samples and we're taking a difference, the margin of error is a little bigger. Both of them can have variability and uncertainty. So that's our, instead of typing 1.96, you can get the actual normal cutoff value here. It's not much difference. It's not going to make much difference, 1.96 versus that, but since we have the computer, we can get that extra decimal place, and it's just about, it's really close, right? You probably wouldn't even report the difference.
Is the difference statistically significant?
Yeah, no, it's not. It's not meaningful to be significant anyway. And so the confidence interval, the lower part is the difference minus up to a difference plus, and those give us values of negative 0.12 up to just below 0. Probably rounded it to 0. So we're 95% confident that the difference is between negative 0.12 and up to 0. So we get our interval, it's negative 0.12 up to just about 0. Right? And it's just a little bit less than 0. So I guess we would conclude that there is a difference that's negative, and we really don't believe that they're equal. Very close to that upper end. Again, our estimate is in the middle, negative 0.06, and the interval is narrow enough to do that. But that's a confidence interval, right? That's a good statement for inference for the difference. Right? The hypothesis test, we're going to go directly at the statement, are they equal or not? Right? So in a hypothesis test, we're going to set up a null hypothesis and an alternative. Right? And the null hypothesis is, are they equal? And this one, are they not equal? This gets translated into our difference by saying the difference is 0 versus the difference is not 0. And if you had some reason for thinking that, that the difference would be greater one area versus the next, right? If you had a social hypothesis that things generate on the coast and take longer time to get to the center, and it's something like technology adoption or something like that. Based on past trends, you might say, oh, it's going to be higher on the coast and slower in the Midwest, and then make it one-sided. Right? But that's not really the aspect of this case, I don't think. Right? So, P1 minus P2 hat is still our estimate. In general, it has the same sampling distribution we wrote down before, but we think about it under the null hypothesis. If the null hypothesis is true, what does the sampling distribution look like? So under H0, P1 hat minus P2 hat is approximately distributed like normal, but now P1 minus P2 is 0. And we could write it as P1, 1 minus P1 over 1 plus P2, 1 minus P2 over that. But they're equal,
Yeah.
right? So let's call that P. Over N1 plus P1 minus P over N2. Right? So that's the, it's not the p value in the other sense of p value. This is the value of p, right? So that's there. Right? So if we want to estimate this standard error, we should do something that combines the samples, right? That does an estimate one thing based on two samples. And the thing that makes sense with a binomial is just to do a composite estimate. You could add the number of successes overall over the number of the sample sizes, right? Another way to write that same thing is N1 times P1 hat plus N2 times P2 hat over N1 plus N2. And that's 0.62, there's 552 in this survey, plus 0.68 and 577 in this survey, and there's 552 plus 577 in that survey. And so it comes out to be about 0.65. These are about equal sample sizes, so it's about in the middle. But if one was a lot bigger than the other, then the composite estimate of the equal numbers would be shifted towards one or the other. So to do our test, we're going to do a kind of a pivot. We're going to take the estimate minus its mean, which is 0, divided by this, and the result is going to be a standard normal. And then we can judge versus the standard normal and don't need to estimate anything else, right? So our statistic is Z. We take our estimator minus 0, right? And so in some contexts, we would think the difference would be something, right? So say you've done past medical studies on rates of relapse with drug addiction, right? You had 2 different treatments. And one treatment seemed to have about a 10% more effective rate. Now you're doing a new study on a new subpopulation, a new area, varying it somehow. Is it still a 10% reduction? So you might have a specific reason to do a certain change, right? If you're looking at income changes, you know, you can think about maybe inflation's at 2%. Is it consistent with inflation or not, right? So then you could have something that's not zero there, right? But then the kind of a easier way to write this thing is to pull out the 1 over n's, and we're going to put our p hats in there. So we're going to get 0.62 minus 0.68 up top, and 0.65, 0.35 down here. And there's 1 over the 552, 522, 1 over 577, and then the square root of all that. Right. So that's our hypothesis test value. And I've typed that into here in R. And so that, one more bracket down here, a negative 2.08. I'll save this file and put it up on the website in case you want to look at it. It's a lot of numbers to write down. But it ends up being negative 2.08. Right? And we compare that to a standard normal. The negative 2.08, oops, cute.
Plus.
Right. 0, and here's negative 2.08. So a p-value that we're going to count is going to be 2 times the tail below 208. Probability that a standard normal z is less than or equal to negative 2.08. I mean, it's twice because the alternative was two-sided. So negative 2.08 or less, or 2.08 if we phrased it the other way, is kind of equal evidence against the null of 0. So a Q norm, negative 2.08, 249, oops, P norm, sorry, is 0.0186. Right? And that times 2 is a p-value, so our p-value is about 0.037. So if we're doing a test at a 5% significance level, which means if it's less than 5% chance into the null, it's unusual, we reject it. Right? So we reject the null hypothesis because the p-value is small, or you could say we reject the null hypothesis because the z statistic is less than the negative 1.96, kind of the equivalent, right? Then we conclude that there is a difference between these two regions. It's a 6% difference. If that's, you judge, is that a meaningful, important difference or not? Right? So we reject the null hypothesis. The regions have, so we reject null 0. The conclusion then is the regions have different proportions. And it would be fine to say something specific, like the Midwest percentage is 62, and the West percentage is 68. Right? You can point out that the data actually says one's less than the other. Right? And that's the hypothesis testing for this in a little more detail. The formulas. Right? But any questions on this? And I always like it if you state hypotheses, statistics, get your statistics and p-values into a conclusion that ties in the statistic and why you're making the decision, and then says what it means in the context, right? Because to me that seems like a fairly complete answer. When earlier in my career, I did grading for a number of years for the AP statistics exam, and so there'd be rubrics, and it would have all those pieces in it, and so it gave me some respect for the high school AP statistics program because they had all these pieces that you had to do to get a complete answer. So we said about using normals, right? But this is an interesting example where continuity versus discrete, continuous versus discrete comes in, right? So when x is a binomial, right, with some sample size and some proportion, x is discrete. X can take on the value of 0, 1, 2, right, up to n. Right? And so the probabilities for this one are at certain points. Right? There's certain masses of probability. So this is x, and this axis is the probability that x equals a value. The probabilities are going to be like this. Right? And also p hat, if you divide by n, right, it's also discrete. It takes on values, 0, 1 over n, 2 over n, etc. N minus 1 over n up to 1. And those are the only places that it has probability. So the graph would look like this. And there's a one-to-one correspondence between individual values. So each one of these probabilities corresponds to one value of x and the corresponding value of p hat. But we write, p hat is approximately normally distributed, centered at p, is p times 1 minus p over n square root as the standard deviation. So he says it's a normal continuous curve. Right? And essentially we're kind of doing a normal approximation. So we're trying to draw a nice smooth normal curve that comes pretty close to these. And the claim is that if you have large enough sample size, then those curves match up really quite well. Even though it's kind of cutting off edges and things like that, it won't be too much. So when we do hypothesis testing and compute a p-value, right? If we use the normal approximation, we're using normal area under the smooth curve, but it only can really have probabilities at points. So that's the nature of this. So if we did a hypothesis that p equals, say, p sub 0, versus an alternative that p, it's easier to do this with one-sided. So for some reason we have p0 and we think it's greater. Right? We observe, right, x, so p hat is x over n. And a p-value, the meaning is what's the probability? Let's assume for now that p hat is greater than p0. So that our alternative makes some sense, right? If our p hat is actually less, then alternative doesn't make any sense at all. Right? But assuming that it is in the direction, it is a little bit higher than like we anticipated, we want to calculate a p-value, right? The probability we get something at x or greater. Right? You can do that with binomials directly. So the p-value is the probability that our random variable is greater than our little number. Well, that's really a sum, and the book writes it with an index of I going from x up to n. Right? So if x is such that it makes the sample proportion greater, if you make x bigger, up to n, up to 1, so the proportion's up to 1, it's going to be bigger values. Right? And given that this is binomial, the probability formula is n choose I, p, now p sub 0, because of the null hypothesis raised to the I, 1 minus p0 to the n minus I. So you can add up those discrete probabilities and actually get a probability. Right? And in this particular example, with one-sided, that's the p-value. The claim is, and if n is big, we can approximate this and use the normal. Right? With computers, either one's about equally as easy, but a lot of times we use the normal. Right? So what happens? So in the normal, if we take, so the normal approximation, if we do the normal, what if we take, we want the probability x is greater than or equal to x. Did I write greater than or equal to over here?
Yeah.
Okay. Right. Well, it's the probability that p hat is greater than our little x over n. And if we model this as normal, and we go directly to the z greater than our x over n minus p0 over 1 minus p0 over n, right, and just go directly to a normal at that x point, right, something happens. We're going to get a little smaller probability, most typically, than if we did the binomial, right? A bit smaller result than the correct binomial calculation. Right. Why is it a little bit smaller? A little bit here. Well, it's a little bit smaller because of the discreteness, going from discrete to continuous. Right? So what this calculation would do, right, is we'd have various bars here, right? And say our x value was here. And the bar around it represents the probability. And if we want to calculate the probability we're greater than that, right, this normal one here takes this point at x and then does the probability area under the line. Right? There. Right? And for the most part, all the way up here, that's pretty, it'll be pretty close approximation to that. But at that one point, kind of cut it in half, right? If the bar stretches 1 unit interval and we do it right at x, we kind of got half that bar. We kind of missed this. We kind of missed this piece in here, right? And the probability at one point might not be that much. It might be 0.03, 0.04. If you have a big sample size, it might be 0.004. But still, you've missed half of it. So there's a chance that can make a difference of a decimal place, a second decimal place, third decimal place. And so, you don't want to miss that. So what can we do to make it a little bit closer to the actual binomial calculation? It's called continuity correction. We could subtract 1/2 from x, right, and do the area all the way there. Right? So this line over here would be x minus 0.5. So instead of calculating the probability greater than x, exactly right at that point, we're going to calculate the probability that we're greater than x minus 0.5. So continuity correction. So if we want the probability that we're greater than our x value, this is exactly equivalent to the probability that x is greater than x minus 0.5. Why are these two things exactly equal? Well, x can only be integers, right? So the probability greater than 35 is the same as greater than 34.7, 34.3, anything in that interval below it, right? And so we're going to take the probability that p hat is greater than x minus 0.5 over n. That little adjustment, and this is what we're going to relate to the z value. X minus 0.5 over n minus our p0. Standardizing, we still have p0 as the mean, p0, 1 minus p0 over n, and the square root of that. So we're going to do this little adjusted thing, and the idea is that it should capture that little extra piece and be just a little bit more closer to the result. Now, at a big sample size, this isn't going to make much difference. Yeah.
I remember this from the other homework, but I was wondering, does it make a difference if you add 0.5 versus subtract?
So it depends on which direction you're going, right? So in this case, we want to include all the probability at a particular x, and we're going up. Right, so we're going to go down to include a little bit more, right? So if you're looking the other direction and you wanted to go down, you would go up a little bit to include the full part of that bar.
Makes sense.
So anyway, that's just the explanation of that. The command, proportion test command, does that for us. And it also does it for the two samples, and it's a little bit more to describe with the two samples, but the idea is the same. So in the other example there that we had, the other day. In 1987, the rate of HIV in sex workers in Malawi was 0.391, right? And then the book said today, so whenever they did a survey, it was 0.480 based on a sample size of 130. And they observed about 62 cases, right? We talked about that yesterday. Based on the reported proportion, we can't quite tell what it is. But let's say it's 62, and that rounds to 0.48. I guess it just said they didn't say 0.480. It's just 0.48 in the book. Right? So if we're asking one side, is it higher? We want the probability that the sample is greater than or equal to 62. The binomial calculation is the density for the binomial. So we can go from 62 up to 130, and the sample size is 130, and the probability we're asking about, the null hypothesis, is 0.391. And so that gives us this probability of 0.0284. If we do the p-norm, the probability, where you do 62 out of 130 is the probability, right? And 0.391 is the mean under the null. And the standard deviation is 0.391 times 0.609 divided by 130. And lower tail equals false. Right, so it'll do the upper one. That normal calculation gives us about 0.22, a little bit lower, right? But if we do the adjusted one, right, we'll because we're going up, we want to capture the full size of that lower bit, so we'll do 61.5. Right, oops. Run that. We have 0.2757. So it's closer, right, to that, and that's the nature of that expression. But any questions on those? One thing, I'll get a next homework posted shortly. The book also touches on matched pairs for proportions. Sometimes this is called McNemar's test. But we will consider this thing on Monday, and you could read ahead in that 8.3 chapter. And we'll talk about some of the 8.2 on Bootstrap T. We had T intervals based on Bootstrap T things, and there's a way to do hypothesis testing with that as well. Instead of talking about that for the rest of the day, we have a new, different topic to talk about. The others that were in my other class who already had this one. And so over the last 2-3 weeks, something like that, there's been some reports of racial propaganda on campus. First, there was a report that some outside group had posted things. This happened last year as well. And it wasn't only at St. Michael's, it was at the University of Vermont, Middlebury, other campuses. And it's not only in Vermont, there's other racial, white supremacists or other racial hate groups, across the US and other states too. It probably exists everywhere. And then some students said there was some graffiti on walls, and it's unclear where that came from. And so you probably know as much as I do. I don't know what rumors are spreading around, but the suggestion was that this affects everybody, and it's worthwhile talking about and seeing if students have any concerns or things that they want to express. And although this is more of a technical math course, the issues of bias, racism, and so on, and ethics are fundamental to statistical practice. So, so my thought about this is that, racism exists. Sometimes it's explicit. A lot of times it's kind of implicit about how people treat other people and react to them and, look at them and do things like that. But I think it's a moral obligation to oppose it and other sources of bias, and then work to, on a personal level, on an individual level, in individual relations, but in a larger context to try and eliminate it, right, and oppose it. And so you can do many things in your life to oppose it, in terms of thinking about yourself, how do you relate to other people. Some people choose to get more exposure to other cultures so they have a better understanding. In part, that's why a lot of liberal arts often have the language requirements. Some cultures on diverse identities. So by appreciating others, you can see their value. At other times, people stand up and do something, go to meetings, go to protests, go to support. Sometimes they talk about it. The other aspect is what do you do in your professional life, right? And so, so does anybody want to say anything about their experience of this, or anyway? But it might be hard to speak up in class, but if you do want to talk about it on a more personal level, you're welcome to have office hours, and we can talk about that as well. Kind of on the professional level in terms of statistics, I mean, we don't talk about it in great detail, but there's a huge apparatus set up for clinical trials and other studies that deals with consent, inclusion of men and women in studies. National Institutes of Health, they have inclusion tables that you have to fill out before, so NIH inclusion enrollment reports look something. Right. That will load. That's not the picture of it. Maybe that's come up as a picture. But anyway, it says how many people in your study do you think are going to be in different ethnic groups, racial categories, male, female, and so on. It asks about children and adults, and so you have to report who's going to be in your study. And often studies, if they are too exclusive, like they focus on one medical center that has a pretty homogeneous population, they might have a hard time getting funded because they're not doing that research. Places like the Census Bureau have a great advocacy for gathering information on different races and ethnicities to be able to understand the dynamics of those populations and the characteristics and their health and things like that. And so in general, there's a strong sense of ethics, I think, at least among professional statisticians, especially those in government and in academics, about paying attention to these things, right? That working on NIH grants, there's yearly training that goes on about not having bias and treating people fairly and informing them and so on. A second aspect of this is there, in terms of professional conduct. So I think professionally there are many aspects where things have come a long way in terms of ethics for protecting and studying the entire population. There's an issue of underrepresentation that's serious and has to be taken seriously. So at the highest levels of research, all race, ethnic groups represented at an adequate level and at a fair level, proportional to their population at least. And over the last 100 years, if not the last 40 years, things have changed a lot. A lot of areas of math and computing and some other areas of science were male, white dominated. But in certainly some changes have happened where many fields are much more equal. Statistics is quite equally represented among graduate students. Biostatistics has been majority female graduate students for quite a while. Certainly there are, I would say, a much greater representation of different race ethnic groups among students and junior faculty than among senior faculty. You know, there's a time element to some of this. Certainly I've worked with individuals of different races and ethnicities. Tommy Wright has been director of statistics research at the Census Bureau for over 20 years, I think now. Professor at Iowa State, African American. A lot of my collaborators are from different countries, Indian, Chinese. I've had graduate students who are Korean. So really statistics and science is international, and people from all over the world make contributions. So being open to that is, and aware of that is important. But it also, do you treat everybody equally? So when we go through hiring new faculty, right, we get coached by the administration about what is fair to consider and what is not. It's not fair to consider somebody's marital status when you're trying to hire them. You can't consider whether they're male or female, or whether they might have children or not. And St. Michael's statement is more expansive than the federal definitions in terms of gender identity and sexual orientation and family heritage and where people are from. And so before every season we think about hiring faculty, we get coached on that and advised. Some places, larger institutions, sometimes have equal employment advisors put onto hiring committees. If there was ever a pattern or suggestion that something wasn't quite right or open with that, then they probably take steps against it. You have to fill out reports. Did you consider everybody equally? Did you make efforts to recruit in different parts of the world? My experience at St. Michael's is that it's a fairly open faculty in terms of different backgrounds. I've worked with students, males and females, African Americans, Asians, others at St. Michael's that have all achieved great success. So that's not necessarily in terms of master's and PhD students that I've had over the years. They come from many different backgrounds. So research is done in these areas to assess bias in employment and education and academics. Are men and women treated fairly and equally as they go for promotion, as they go for salary increases? And a lot of the research is really hard to do because you're trying to assess, given all the information people have where they're making decisions about hiring and promotion, is it fair? And it's a very, there's a lot of different measurements of accomplishment within that. That said, there could still be pockets of bias and people that treat people differently, and so it's a subtle thing. Like, do you tend to offer certain service opportunities differently to men versus women? Do you do things like, if there's a minority member on the faculty, do they tend to be on the diversity committee? Is that right? Should they be on the diversity committee? What if they don't feel inclined to doing that? It's so some of the things that might come across as well-intentioned, thinking through those things is challenging. But generally, I think that it is a good time because things are opened about women and minorities participating in all different aspects. There's still support to give scholarships to help equalize things that historically haven't been quite as equalized. There's still outreach. And there's some things that can be done at the college level and beyond, but some of it's really the pipeline. So those of you who are going into education are going to be interacting with young children, right? When do people start dropping out? Why do you get fewer African American PhDs serving on National Academy panels than the proportional representation? Why is it less, every step along the way? Why does the proportion seem to shrink? Well, some of it could have started earlier, and some of it could be, if some of the schools early on are not equal, or showing role models, or promoting the idea that certain groups can go in. If the message just isn't coming across strongly enough, then it's will have impacts all through society. And I think things are changing. If you ask where are the women in science and minorities in science, they've always been there. It just maybe they haven't been as promoted as enough and in quite as many number, but they've always been there. And so I think societal forces will keep pushing forward, and as long as we express the interest that we support a diverse workforce in science and technology, then I think society can be changed for positive ways, and everybody can benefit by having a richer, more diverse, more robust workforce for studying things in science and technology and other fields. So, but anyway, so it's an important issue. It's always going to be here. It's always going to be at other campuses too. And so saying a few things about it, there's certain classes where it's focused on diversity and different experiences of minorities and so on. But it has relevance for us too. But any comments or thoughts? One thing that was brought up in the other class is that some data sources, sometimes police data or health data or economic data of some sort, or evaluation data of performance. And sometimes those data sources from the past have some sorts of bias built into them, right? So where do police do the most stops, the most arrests, find the most crime? Well, it's really where the police are going, right? If they're targeting certain areas and holding a very high standard there and are predisposed to arrest people in certain areas, they get more arrests. So say you use that data to predict where they should go next and where they should be on the lookout for crimes and things like that. So the data from the past, if it's used in certain ways, can inform and kind of carry over a bias, even if it's not meant to do that, even if the people now making decisions think, I'm going to be objective, I'm just going to use data. Same thing for health and medicine. If the treatment given to certain race ethnic groups was inferior to what it was for others, well, maybe their evaluation of spending money on them is not going to come out as good, right? So there's some evidence, that minorities are offered certain types of treatment at lower rates. Well, if that makes other treatments look less advantageous, then there might be conclusions that they aren't needed, right? So it could kind of reinforce things. So it's tough to overcome, right? So it's careful looking at data and what could possibly have influenced how things go. So that kind of aside, something different than the others. So kind of a personal response, but also part of this profession, which I think is robust and has people with great intent in overcoming or lessening the impact of some things that have gone wrong in the past. So. But that's it. So we'll come back on Monday, and we'll be talking about hypothesis. Yeah, thanks. Do you have the homework? Sort of put that here.
Should we do
Thank you.
I'm not sure when I got my second email, but I was just not able to
Right.
get it to you. So I did the
I didn't download.
Right, say it right here.
It didn't go down until 8 a.m.
Yeah,
I sort of like retried it 3 times and
I was doing a lot of it last night.
Thank you.
The RC was.
There was one problem with a little bit of
Yeah.
code, which was, I
Oh,
found
the
this.
phones
And I
got-
don't know how it got in there, but that's mistyped, right? So it's out, one letter came out.
oh,
right? So if you run that,
Yeah.
um,
Yeah, I finished. I finished the first 3 problems
okay,
on Lawrence.
so if you get there, and then that's fine.
The last
Now it
one.
does a summary.
Yeah,
Oh,
so
wow,
that's
yeah.
where I needed to
Yeah,
go.
so, see,
how is
I don't know
it?
how that got in there, because I had typed it and then run it,
My luck.
and then at some point,
Like with the last
Yeah, I
one,
didn't even
I-
think
yeah.
to try to catch that.
Just type.
Can I, because
Was it
it's
typo?
it's
Like,
just
there's
problem
like a-
5, I have the
Right.
rest of it done, can I just turn it in on Monday then, or
yeah, sure, that'd be
Yes.
fine.
do you
Yeah.
want the rest of it now?
Yeah, I found that one. I was
Did you write part of 5 on that one, or do you want to just, do you want to just give me that one that I can add in the points you get for 5 on?
Yeah, actually 5 is has.
Yeah, no, I know
this one,
what
so I'll
you
just
write
put that
in
in now to the final
Yeah.
Monday.
That sounds good.
Thank you.
Yeah, no, I noticed that this morning.
Yeah.
How are we going?
I was trying to figure out, because I had read
Yeah,
looking
you
in
know,
for the other
it looks like
one,
you were, you know, just kind
fine.
of glancing through that, it looks like you're trying things that you need to do, but,
Yeah,
and,
thank you.
it took me a couple, like, what happened, and
Yeah,
then-
thank you.
Yep.